Find the exact length of the curve x is equal to 5 plus 6t squared, y is equal to 1 plus 4t cubed, where t goes from 0 to 1, and at which points on the curve does the tangent have a slope 1. So the arc length for our parametric curves goes from alpha to beta of the square root of our first function x, the derivative of that with respect to t squared, plus the derivative of our second function y with respect to t squared as well, dt. So let's find our derivatives. The derivative of x with respect to t is going to be equal to 12t, and then the derivative of y with respect to t is going to be equal to 12t squared. And of course, our alpha just goes from 0, and then our beta is equal to 1. So if we plug this all into our integral, we'll have 0 to 1 of the square root of 12t squared plus 12t squared dt. And now if we begin to simplify this, of course, we'll still have 0 to 1. And then 12 squared is 144. T squared is t squared. Plus, again, 144. And then t squared is going to be t to the 4th power dt. And we can do some factoring on the inside. So we can take out 144 t squared from both of those, and we'll be left off with 1 plus t squared. And then we can see that our 144t squared, we can just take out a 12t out of our radical. So now that we know what that simplifies to, let's begin to evaluate. So we'll have 0 to 1 of 12t times the square root of 1 plus t squared. And then let's just perform a u substitution. So we'll let our u equal to 1 plus t squared. That'll make our du equal to 2t dt. And then of course, we'll have 1 over 2 du is equal to t dt. And let's make some room. So if we take this 12 out of our integral, we'll have 12 going from 0 to 1 of t 1 plus t squared dt. And now you can see that we have our t dt and our t dt in here. So that means we can substitute. And then I forgot, let's figure out our new limits. So if we plug in 0 to our u function that we substituted, we'll have 1 plus 0 squared, which is equal to 1. And then if we plug in 1, we'll have 1 plus 1 squared, which is equal to 2. So then our new integral has 12 times 1/2, going from 1 to 2, of u du. So now if we just simplify this, we'll have 6 of 2/3 u to the 3/2 power, going from 1 to 2. If we take out our constant of 2/3, we'll be left off with 4 times u to the 3/2. So then if we remember our trick of where any number to the 3/2 power is just the same as that number times the square root of that number, we can reduce this even further. So we'll have 4 times 2 square root 2 minus 1 square root 1. And then this 1 square root 1 can just reduce down to 1. And then that's our length of our curve. So now for part B, we need to find at which points on this curve is the slope equal to 1. And we could do that by finding our slope. So if we remember that our slope for parametric curves is going to be equal to dy over dx, which will be dy over dt, or the derivative of y with respect to t, over the derivative of x with respect to t. So what this is saying is the slope of our parametric curve is equal to the slope of our y function over our slope of our x function. So our derivative of y with respect to t was 12t squared. And then our derivative of x with respect to t was just 12t. We see our 12s and this 1t cancel. So we're just going to be left off with t. And then we said in our problem that our slope is equal to 1. So we'll have our slope is equal to 1. So now that we have a designated slope, we can plug that into our x and our y's to figure out which point on the graph that our slope is equal to 1. So we'll have x is equal to 5 plus 6 times 1 squared, and our y is equal to 1 plus 4 times 1 cubed. So this one's pretty simple. 1 squared is just 1, so 5 plus 6 is equal to 11. And then for our y's, 1 cubed is still 1, so 1 plus 4 is equal to 5. So that means on the point 11, 5, our slope is 1. And then that's the answer to both of our questions.